Assalamualaikum warahmatullahi wabarakatuh. We are Team Cybertron for the EEE 4308 Digital Electronic Snake and Ladder project. These are our teammates, and we have all worked valiantly throughout the months to give you this project. We hope you will all enjoy it. Thank you. Assalamualaikum. My name is Mohammad Najagatiram, and I will be explaining the board module of this project. In this project, we decided to use the dot matrix configuration for the LEDs. In dot matrix configuration, all the anodes of a row of LEDs are connected together, while all the cathodes of a column of LEDs are also connected together. All the rows are connected to a 2x4 decoder, which is active high, while all the columns are connected to a 2x4 decoder, which is active low. The position of the LED that will be turned on is determined by a 4-bit binary number. The first 2 bits of the binary number controls the row number from bottom to top. Therefore, this is 0001 1011 row. Whereas the last 2 bits of the binary number controls the column number from left to right. Therefore, this is 0001 1011 column. When all the LEDs are deactivated, as the column decoder is active low, therefore when it is deactivated, it outputs a high potential. And whereas the row decoder is active high, when it is deactivated, it outputs a low potential. Therefore, all the LEDs are reverse biased. When we enable the decoders, we can see that for the 00 row, the row decoder outputs a high potential. Therefore, all the anodes are active high, whereas the column decoder outputs a low potential for the 00 column. Therefore, all the columns here are low potential. The intersecting part of the row and the column is in this LED, which is forward bias, and it has turned on. Meanwhile, all the other LEDs are remaining off. As you increase the value in the column decoder, the LED goes from left to right, while increasing the value in the row decoder makes the LED go from bottom to top. In the current configuration, the LED always goes from left to right when we increment the column values, but in our board module we have to make it so that for the first row it goes from left to right, and in the second row it goes from right to left. Similarly, in the fourth row it has to go from right to left. This can be achieved if we add additional circuitries in the input of the decoders. We achieve this desired result by using 2 additional XOR gates for each color. Here we can see for the first row it goes from left to right, but for the second row it goes from right to left. Similarly, for the fourth row it also goes from right to left, but on the third row it goes from left to right. An issue with the dot matrix configuration is that it cannot light up 2 LEDs at the same time, which is problematic for us as both the snake and ladder requires 2 LEDs to be lit up simultaneously. This issue can be bypassed by using a multiplexer whose select pin is connected to a high frequency clock. As the clock toggles, the multiplexer will toggle between 2 values of the LED very quickly, which will make it seem that the LEDs are lit up simultaneously. For demonstration purposes, the clock has been slowed down here. After combining all the aforementioned circuitry and logic, we finally reach the board module. Here we can see all the different decoders for the LEDs, starting with player 1, player 2, ladder, and snake. In here we input the various user given values for the ladder and snake. For the ladder, we use an adder to determine the ladder end and use a multiplexer to show both points of the ladder. Similarly, we use a subtractor to determine the snake end and use a multiplexer to show both points of the snake. This concludes the overview of the board and position module.
Assalamu alaikum. I'm Azmain Nasif, ID 347. I'm gonna discuss the logic module part of the game that we made. So the logic module basically determines the next position of the player given the initial position of the player. So before discussing the main circuit, that is this whole part of the logic module, we should discuss the game start condition of the logic module, which is this part. So we all know to start the game, a player must roll 1. Until the player gets 1 as the dice value, the player cannot start the game. This condition is basically ensured by this circuit. So if the player is at initial position, that means 0000, then and the player's dice value is not equal to 0 1, so the player's dice value, let's suppose 2 or 3, then the player won't be able to move to the next position. So the dice output value eventually will be equal to the ground value here. So the multiplexer will pass the ground value instead of the actual value of the dice. But if the player gets 1 as the dice out value, then the output value of the dice will be the dice 1 and dice 0, which is the actual value of the dice. So the player will be able to move to the next position, or the player will be able to start the game. So this basically ensures the game start condition. Now let's see some demos of the game start condition. Let's suppose the initial position of the player is at 0000, and the dice value is suppose 2. So we should get the output 0000 as the player hasn't rolled 1. So as you can see, from starting the simulation, the dice output is 0000. Even if the dice value is 3, the player position is at 0000. Only if the player or dice value is 1, so 1, then the player next position is 0001. So this ensures our game start condition. Now, before discussing the main part of the logic module, we should discuss some key terms like S, A, D, B, and C. So S is basically the sum of the initial position and the dice output. This is an error. This sums up the initial position and the dice output, and we get it as S. Now, A basically ensures whether the ladder end and the S that we got from here are equal. So this is a comparator. This ensures whether they are equal or not. D basically is another comparator which ensures whether the ladder end and the snake end are equal. B is another comparator that ensures whether S and snake head are equal. C is another comparator that ensures whether our snake head and the ladder head are equal. Now, the player can end up in 4 possible positions, which I have given here. So the player can end up in S, which is initial plus dice, or he can remain in the initial position, or the player can end up in the tail of the snake, or the player can end up on the head of the ladder. Now, depending on where the player lands, I have given the selector inputs. So this selector input is basically the selector input of this mask. So here are four into one mask, and the selector inputs are these inputs. So if S is the final condition, then the selector input should be 0 0. If initial position is the final condition, then the input should be 0 1. If snake tail, then 1 0. If ladder head, then 1 1. Now I have considered the first digit of the selector input as LSB. Here, the first digit of the selector input is LSB, and the second digit of the selector is MSB. Now, in order to implement the MSB and LSB, I have made a truth table. So this is the truth table for the MSB, and from this truth table, I have got the expression of the MSB. That is this, uh, and I have implemented the expression of the MSB here. So this is the expression of the MSB using logic circuits. Now, depending on the values of MSB, whether the MSB is 0 and 1, LSB expression changes. So if the MSB is 1, then LSB is this. So this is the truth table for the LSB, and this is the final expression simplified form of the LSB when the MSB is 1. I have implemented this expression here. Here is the implementation of this expression. Now, whether if the MSB is 0, the LSB is just equal to the carry. I have given it here. So if the MSB is 0 here, so 0 get passed, the carry will get passed as the LSB. And if the MSB is 1, the LSB value will be this output, so this will get passed as the LSB. So let's see some demos of the circuit. Let's suppose the player gets eaten up by the snake. So let's suppose the snake head is at 3 and the snake end is at 2, and the player's position must be at 3 as the player gets eaten up by the snake. So 1 for the dice and 2 for player position. So we should expect the output value should be 0010. We should expect the output value to be 0010. Let's see. As you can see, the output value is 0010, which is equal to the end of the snake or the tail of the snake. Now let's stop the simulation, and let's suppose the player climbs up the ladder. So the player should position should be equal to the ladder end. So 1 1, and the player ladder head suppose 8. So the players at the end should be at 8. So let's see. As you can see, at the output is 8. So the player is at the ladder head, which is 8. Now let's stop the simulation and let's consider an edge case. So let's suppose the snake head and the ladder head are equal and the snake end is 2. Now the players at first is at ladder end. So the player climbs up the ladder and the player reaches the top of the ladder, which is 8. Now at the top of the ladder there is a snake. So the snake eats up the player. So the player's final position should be 0010, which is equal to 2. So let's see, the output should be 0010. As you can see, the output is 0010. So that was my part of the game that we made, which is the logic module. I hope I was able to give a clear understanding of the logic module. Thank you.
I'm gonna demonstrate the memory module, player selection module and the dice module that are being separated from the main project for a better understanding. So I'm beginning with the dice module. So I have made an 1 to 3 up counter using the JK flip-flops, and the state table is here. 00 is used as an unused state and the Carnot map is here. So using this JK inputs I have made this circuit, and the clock pulse of the JK flip-flops are taken from the Smith trigger oscillator, and the output of the oscillator is taken to an AND gate, and the other input of the AND gate is taken to the dice roll. So when I am pressing the dice roll, and the oscillation will pass to the clock pulses of the JK flip-flops, and the JK flip-flops will make triggering. But I need a stable value for dice 0 and dice 1 that will be passed to the snake ladder logic module. So I have used a NOT gate here with the dice roll, so that when the dice roll is released, the NOT gate will pass in 1 and the AND gate will pass the value of the JK flip-flop to the dice value. And also the JK flip-flop output are taken to the 7447 IC, and the 7 segment display is used here for the display. So now I'm gonna discuss about the player selection module. JK flip-flop is used here, and the J and K input is taken as 1 so that the toggling operation can happen, and the CP is used as a clock pulse. So CP is the node from the dice roll. So when I'm pressing and releasing the dice roll, the CP will be triggered from 1 to 0, and those triggering will make the LEDs toggling operation. So and the CP prime is taken as another node. This will be used in the memory module. So thus the player selection module is used here, and this is the reset module that I will also discuss later. So memory module, here I have used two PIPO registers for the two players. So before that I am going to discuss about the comparators. So this is the player current position, player 1's position, player 1's position and player's 2 position. Player 2's position are this. And so for the CP prime that I have taken from the player selection module, the CP prime will make the decision of which player's position will be passed to the snake ladder logic module. This position pose 0 1 2 3 will pass to the snake ladder logic module for the current player, and this is the snake ladder logic module I have assumed this as a snake ladder logic module. The current position of the players will be passed here as the input, and the dice will also have an input here. So after the snake ladder operation, the updated position will be this. So this is going to be the input of the two registers, player 1's register, PIPO register, and the player 2's PIPO register. So the inputs are this. So at a time the one player's position should be updated. So the clock pulse is taken here for the exact operation. CP prime is also used here for the operation of the clock pulse. So CP prime is taken from the player selection module. So and I have used a delay here. Why I have used a delay here? Because current position should have to go to the snake ladder logic module, then snake ladder logic module had to make the operation here, then it should pass the updated position to both of the registers. So there should be a delay of very small time period. So I have used a very short delay here of 2.2 millisecond. So after the delay, for any of the player's position, for the correct position will be passed to the exact player's updated position, and these positions will go to the board module. This will update the board module. So how is it working, we will understand after the testing. So now I am beginning the testing. So first of all I am taking some random values for a better understanding. So now player 1's position is 3 now. and now it is player 1's turn. So for player 1 the CP prime is now 1. Okay, so CP prime as 1, but after the dice roll of player 1 the CP prime will move to 0. So for the CP prime equals to 0, the player 1's position will be transferred to the pos 0, 1, 2, 3, and pos 0, 1, 2, 3 will move to the uh, snake ladder logic module, where the operation with the dice rolls will be done, and the updated position, this is the updated position, will move to the both of the registers. So here the clock pulse is triggering from 1 to 0. Now we need the shift of the updated position to player 1's position, so we need a shift of this memory. So for 1 to 0 shifting of the CB prime, the for using the NOT gate, this will pass 0 to 1 shifting. So as it is a positive edge triggered register, so it will shift the updated position to the player 1's position. But for player 2, as it is a 1 to 0 shifting, it is a positive edge triggered clock pulse, so it will not shift the updated position, rather the position of player 2 will be stored here. So thus it is working, and the reset button is used here for connecting with master reset. So while I am pressing the reset button, the master reset will be working, and the both side of the input and the output of the registers will get 0. So now I am gonna take an operation, and player 1's position is now 3. So let's take some value 2. So now player's position should be 5. So now it is seen that yes, this is 5. So thus the modules are making this happen. And for the triggering, after the triggering, so I am getting the stable value 2 as the dice 1 and dice 0, and the player selection module, as player 1's turn was happened, so player 2's turn, player 2's LED is now on, as it is the current position's turn. So thus the modules are working very well. So thank you.
Assalamu alaikum everyone, this is Muhammad Intikhab Mahmood. In this portion of the video, I'm going to talk about the winning module. So basically, the winning module checks whether the game is finished or not, and also we can tell who the winner of the game is. To decide that, we used two 4-bit comparators here. This one checks whether player 1 is the winner or not, and this one is for player 2. So let's see here. This is the position of player 1. This is MSB and this is LSB. And this is the winning position, which is 15. Let's assume that player 1 has reached the winning position. Then this A equals to B will be satisfied, and this QA equals to B output will have 1. Since we used an OR gate here, we can say that if one of the inputs of the OR gate is 1, the output should definitely be 1. So we don't need to care about the other input of the OR gate. So this terminal of the buzzer will have 1, and this is grounded, so it is 0 definitely. So the buzzer will have a kind of potential difference, so the buzzer will be activated, declaring that player 1 has won the game. And this situation can also be explained for player 2 as well. If player 2 has reached the winning position, then this output will have 1, and it will pass as an input of the OR gate, and the OR gate's output will be 1, and this buzzer will again be activated, declaring that player 2 has won the game. So I can demonstrate with an example here. Here in the board module, we can see player 1 has reached the 15th position. So if I turn on the simulation here, we can hear a sound. That means the buzzer has activated, declaring that player 1 is the winner and the game is finished. So this is the winning module. Thank you.
After combining all the aforementioned modules together, we finally reach the fully integrated snake and ladder circuit. Here we can see all the different modules such as the board module, position decoder, logic module, memory, winning, player selection, and dice module. For connecting all the modules together, we use terminals given in Proteus to make the connections much more easier to understand. When a dice is pressed, the dice value and the current position value is fed into the logic module, which then gives an appropriate output, which is then stored in the memory module, which is then fed into the position decoder. which displays it on the board. Player selection module toggles between the two players each time the dice is pressed, and the winning module plays a sound in the buzzer when the final cell has been reached. It should be noted that the speed of the dice module here has been reduced significantly for demonstration purposes. We can increase the speed by changing the resistor and capacitor values of this inverting Schmidt trigger oscillator. By providing these values, the clock will oscillate at 70 Hz, which will make it very difficult for a player to dictate a desired value. Now we will be showing the live demonstration of the project. It should be noted that the yellow and green LEDs are flickering due to the limitation of the dot matrix configuration mentioned in the board module segment. Furthermore, it should be also noted that in real life this flickering would not be as prominent, but it is prominent in Proteus due to the software limitation and the limitation of my own hardware. It should be also further noted that the rate of the dice module has been reduced significantly, so we can choose our desired values to showcase different features of the project. Now we shall begin. The player should only be able to progress if they roll a 1. As you can see, player 1 has rolled a 1 and is progressed by 1. Meanwhile, player 2, if it rolls 3, it cannot progress unless and until it rolls a 1. When it rolls a 1, it can enter the board and then progress normally. Now we will show the ladder function of the board. As you can see, player 1 has progressed up from 2 to cell 14. Now we'll try to get player 2 onto the board. As you can see, player 2 has reached the board. Now player 1 will not be able to win the game unless and until it rolls a 1. So as you can see, rolled a 2 and has not been able to progress. Now we'll try to use the player 2 to show the snake operation of the game. As you can see, as rolled a 2, so player 1 was not able to progress. Player 2 has rolled a 3 and has gone forward by 3. Player 1 rolled a 3 and as such was not able to progress. As player 2 rolled a 2, it entered the snake mouth and has gone down to the snake tail. Now, if player 1 rolls a 1, it should be able to win. Player 1 rolled a 2 and player 2 has rolled a 1. As you can hear, the player 1 has rolled a 1 and has been promoted to the winning cell, and you can see the buzzer is going on from the winning module. Now we will be showcasing two special cases, first of which is if the snake's tail and the ladder's beginning is on the same cell. As a result, if a player were to land on the snake's mouth, it should go down the snake and then climb back up the ladder up to cell 13 in this case. So first we need to bring the players on the board by rolling a 1. Player 1 is on the board. Player 2 is also on the board. Player 1 has progressed by 3. Player 2 has also progressed by 3. Now if player 1 were to roll a 1, it should go down the snake and then up the ladder. As you can see, the player 1 has gone up to cell 13. We'll be showcasing another special case where if the snake's mouth and the beginning of the ladder is on the same cell. In this case, the player should prioritize the ladder over the mouth and it should go up rather than down. So if we were to roll a 1, we would see that the player 2 has also gone up the ladder instead of going down the snake. Now if we were to player 1 has progressed by 1 and player 2 has progressed by 2 and has won the game, as you can see from the winning module. This concludes the whole project overview from Team Cybertron. Thank you for watching.